This is Jae-Sung, and I am very glad to present my work in Interspeech 2022. These are my co-authors, and please note that this work was performed while at NCSoft. First is the introduction. Text-to-speech is a typical one-to-many mapping problem because humans speak speech in a diverse way. Recent NAR-TTS models can be divided greatly into two. One is the autoregressive TTS model, and the other one is the non-autoregressive TTS models. NAR-TTS models have best inference speed and robustness. However, the performance gap between the AR-TTS models and a lack of diversity exists. This is because the NAR-TTS model cannot use previously generated acoustic features as context, and therefore the one-to-many mapping problem becomes severe. Therefore, in this work, we aim to improve the naturalness and diversity of the current NAR-TTS models by improving prosody modeling and alleviating the one-to-many mapping problem. Prosody modeling is a crucial factor in alleviating the one-to-many problem and improving the performance of TTS models. There are two kinds of prosody modeling approaches. First is supervised prosody modeling with defined prosody features. FastSpeech and FastSpeech 2 model is one of the famous supervised prosody modeling approaches. They model the variance information of speech with explicit prosody features such as pitch and energy. However, the prosody information that is intrinsically presented in speech, for example, emotion, may not be modeled. The another one is the unsupervised prosody modeling approaches. They represent the variance information of speech into latent variables. When we take a closer look to unsupervised prosody modeling approaches, there are three mainstream. First is the global scale prosody modeling approaches. They model the translevel speaking style of speech in a single latent vector. However, the locally varying prosody, such as accents, may not be modeled. Second is the local scale prosody modeling approaches. They can model the locally varying prosody. However, they cannot generate a speech with a consistent speaking style because of the absence of global scale representation. The last one is the multi-scale prosody modeling approaches. This approach tries to take advantage of previously two approaches. However, in the inference space, a reference speech that contains a similar text content to an input text is necessary to generate a speech with natural prosody. Because the VAEs are a class of probabilistic generative models, we think that they are suitable to handle the one-to-many mapping problem of TTS. And also they have an advantage that the reference speech is not required in the inference space. The NAR-TTS model incorporated with the single-scale VAE modules were proposed. However, in our preliminary experiments, the expressiveness of the single-scale VAEs was limited. The TTS models incorporated with the hierarchical VAE architectures have also been proposed. However, they have been only studied with the AR-TTS models. To improve the naturalness and expressiveness in NAR-TTS models, several previous approaches adopted the hierarchical structure. However, in our previous work, we only focused on improving naturalness and intelligibility of the NAR-TTS models instead of prosody modeling. In other previous works, they only the predefined prosody features are modeled in supervised manner. Taking advantage of the aforementioned prosody modeling approaches, we propose an NAR-TTS model with a hierarchical and multi-scale VAE to better address the one-to-many mapping problem in the NAR-TTS models. We conjugate that the prosody of speech should be modeled in multi-scale and with hierarchical structures. So the global scale prosody, such as overall pitch and speaking speed, should be determined first. And then the local scale prosody, such as intonation within a word, duration of a phoneme, and pauses between words should be modeled depending on it. We also adopted the adversarial training technique to further improve the speech quality. And through the experiment, we verified that the high-move TTS model generated generates more diverse and natural speech compared to single-scale VAE-based TTS models. In addition, we showed that the different prosody informations can be represented in each scale of the high-move TTS model. Next is the proposed method. The overall architecture of high-move TTS model is shown in Figure 1. For the baseline TTS model, the fifth speech model was used. The phoneme embedding Y is first encoded into hidden representation H. The proposed high-move encoder encodes the mel spectrogram X into a prosody embedding Z condition on H. The phoneme level duration and pitch values were predicted from H concatenated with Z. The predicted pitch values are embedded through 1D convolution and added to H concatenated with Z. Then it is length regulated with the predicted duration, and finally, the regulated representation is then decoded into mel spectrogram. The discriminator predicts whether the input is real or fake and used for adversarial training. The reconstruction loss of the predicted mel spectrogram, duration, and pitch values are as follows. Now let me explain the detailed architecture of the high-move encoder. Because the high-move encoder has hierarchical and multi-scale structure, it first extracts the prosody information from the mel spectrogram through mel encoder and predict the posterior mean and standard deviation vector of global scale prosody ZG. Then we concatenated the replicated ZG and H and form HL through hidden encoder. Next, the multi-head attention layer learns the correlation between HG and HL and outputs the phoneme level features. The posterior mean and standard deviation of the local scale prosody embedding is then predicted from them. Note that the ZG and ZL are sampled from the normal distribution as follows. And finally, the replicated ZG and ZL are concatenated and become the final prosody embedding set. Also, the prior over latent variables of both scales are assumed to follow a standard normal distribution. The model is optimized with the evidence lower bound as follows. We also adopt the posterior mean predictor. Similar to previous work, we train the explicit predictor that predicts the posterior mean of local scale latent variables to generate natural speech. Stop gradient is adapted to prevent the posterior mean predictor from affecting other parts of the model. And the posterior mean predictor loss functions are as follows. To improve the perceptual quality of the generated speech, we adopted the adversarial training technique. The architecture of the discriminator is similar as that used in our previous work. We used the following least squares loss for the adversarial training and an additional feature matching loss for training the generator. And the final loss functions of our high-move TTS model is as follows. Next is experiment. For the experiment, we use the LJ speech dataset, which is a single female speaker dataset with about 24 hours. The 1% of dataset was fully for testing, and the prosody features are extracted from the Montreal Force Alignment Tool and Pratt Toolkit. The detailed high-move TTS model configurations are as follows, and the further details can be found in the paper. The detailed training setups are as follows. We choose 4 models as the comparison model. First is the best speech model, which is the baseline NAR-TTS model. Second is the GAN speech model, which is adopted the adversarial training technique to fast speech model. Next 2 models are the global scale VAE and the local scale VAE models, which is the single scale VAE based models. For the fair comparison, we changed the baseline TTS model of all comparison models to the fast speech model. First, we evaluate the sample diversity of each model and verify the diversity improvement of the high-mode TTS model. For the evaluation method, we synthesize 100 different speech samples from the GVAE, LVAE, and high-mode TTS models for each sentence in the test dataset. Then the standard deviation values of the utterance length, average energy of utterance, average pitch of utterance, and pitch standard deviation within utterance were computed for each sentence and averaged through the test dataset. The result can be found in Table 1. The LVA model had the highest standard deviation values in sigma p. This was because the LVA model focused on the local scale prosody features, and the pitch is the most locally varying prosody features compared to others. However, it resulted in extremely unnatural speech, which will be presented in Table 2, because the LVA model could not generate speech with temporally consistent pitch contour. Also, the high-mode TTS model could achieve the high standard deviation values, generally for over prosody features, which means that the high-mode TTS model can generate speech with a high diversity and could well represent the various prosody attributes in a hierarchical and multi-scale way. Secondly, we analyze the latent representation of each scale to observe what information is represented in each scale of prosody embeddings. The high-mode TTS model sampled in ZG but with fixed ZL denoted as a high-mode TTS-G model. And the high-mode TTS-L model is the opposite model. The high-mode TTS-G model had high sigma p and sigma p values, while those of high-mode TTS-L were low. This was because the high-mode TTS model modeled the transferable prosody attributes such as tone or speaking speed into global scale prosody embeddings, ZG, and the remaining locally varying prosody was modeled in ZL. Besides, the utterance length was varied by both scales of latent variables, but was changed for different reasons. The overall speaking speed of generated speech differed by the sampling in the global scale, and meanwhile, the sampling in the local scale varied the short pauses while the overall speaking speed was preserved. This can be also shown in Figure 4. To evaluate the intelligibility of the model, we computed the WER values for each model with pre-trained ASL model. The WER result of the high-mode TTS model were slightly higher than the GAN speech model because of the diverse speaking style generated by the high-mode models. The high-mode TTS model with the temperature values, which means that the global and local scale prosody embeddings were set as the prior mean values without sampling, achieved the lowest WER result. The GVA model achieved the low WER results. This was because the speaking speed was commonly lower than the other models, and also because that the GVA model had low diversity. For the subjective evaluation, we conduct the MOS test. The high-mode TTS model achieves similar MOS result as the best speech and GAN speech model while generating the speech with diverse speaking styles. The LV model has significantly low MOS result because of the inconsistent prosody of generated speech among the text sequences. Finally, the high-mode TTS model achieved the best score with temperature value 0 because we alleviate the onto-many mapping problem of the TTS model. Finally, for the conclusion and the future work, we propose a hierarchical and multi-scale VAE architecture to generate diverse and natural speech for the NAR-TTS model. The high-mode TTS model determines the global scale prosody first, and then determines the local scale prosody of speech via conditioning on the global scale prosody and a learned text representation. By modeling the prosody of speech in hierarchical and multi-scale ways, And alleviating the one-to-many mapping problem of speech via VAE, the HiMap-TTS model can generate speech with high diversity and naturalness. For the future work, we would like to expand the experiment to expressive or emotional speech dataset to further verify and analyze the effect of the HiMap-TTS model. Demo samples can be found in the following link and the QR code. Thank you for listening.